All right, welcome to 7.5 Systems of Inequalities. This is our last unit, or our last section in Unit 7 or Chapter 7. Last of our systems. So what we're going to be doing is we're going to be doing a little bit of graphing, and we're going to kind of go back in time and look at some of the stuff we learned in Algebra 1, and hopefully extend it a little bit into deeper understanding of this concept. All right, so let's go ahead and take a look at the first piece. Let's just figure out how to graph a linear inequality. All right, so first of all, you need to graph the line. And when we graph the line, we obviously graph on graph paper. And when you graph the line, you have to make the determination if the line is solid or dashed. A dashed line represents something that doesn't exist, and a solid line is something that exists. So on a dashed line, that's for things that are either less than or greater than. Because it doesn't equal the line, we have a dashed line. It's solid, therefore, when it's less than or equal to or greater than or equal to. Okay, that's just when we graph the line. After we graph the line, we're going to shade the region that contains the solutions to the inequality. We're going to call that our solution set. Every single point that's in the shaded region is a solution to the inequality. Oops. So let's take a look at what that is going to look like. Let me put this back up here. Less than, greater than, less than or equal to, greater than or equal to. Let's think about y is greater than or equal to 2x plus 3. So if we were to sketch this graph, sketch as in like an upper division math student does, not like an Algebra 1 student, we know that the y-intercept is 3, and we have a slope of 2. So if we go up to 5 and down to 1, something along this line will happen. We go through y equals 3. It rises 2 and runs 1. It drops 2 and runs backwards 1. And we have the 3 dots that create our line. Now, because it is a greater than or equal to, we get a solid line. But that is not the entirety of the problem. What we need to do is we need to determine what side of the line gets shaded. Now, there's a couple ways to do this. The first way is to just test a point. So notice we have above the line and we have below the line. A really nice point to test is 0, 0. So if I plugged in 0 greater than or equal to 2 times 0 plus 3, I can ask myself, is 0 bigger than or equal to 3? And because this is a false statement, we shade on the other side. And let's test something out here. Let's test the point 0, 5. So if I plugged in 5 is greater than or equal to 2 times 0 plus 3, 5 is definitely bigger than 3, and therefore we shade above the line. And you can just do shade like this. This is fine with me. You can get all fancy and do a lot of shading. It doesn't matter to me, as long as you have indicated where the solutions are. And any one of these points that I choose out here will make a true statement if I plug it into the inequality. And anything that I plug in down here will not work. Let's try something else. What about y is less than negative 2? So first of all, you have to think and remember, what does the line y equals negative 2 look like? It's a horizontal line at negative 2. Because it is strictly less than, no equal to sign, this is a dashed line. We've got to make it dashed. And we want all y values that are less than negative 2. We could plug in a number if we want to. We can plug in the point 0, 0. And we can ask ourselves, is 0 less than negative 2? And that statement is false. So we need to shade below the line. And we should know that every y value below negative 2 is less than negative 2. We could also do something like this. X is greater than or equal to 1. Well, that's going to get something like this. At x equals 1, we have a vertical line. It's solid because it's equal to. And we're looking for x's that are greater than 1, so we're looking for this direction. All right. What if, however, though, it was looking like, what if it looked like 2x plus 5y is less than, let's just go strictly less than 10. Now, a lot of people forget how to graph this type of line, but what we can do is we can find x and y intercepts. So if x equals 0, y would be 5. So my y-intercept is 5, or sorry, not 5, 2. Sorry about that. If I plug in x equals 0, y would be 2 as a y-intercept. If I plugged in y equals 0, I get x is equal to 5. There we go. And then because it's strictly less than, we're looking for a dashed line. Oops. Let's try that again. There we go. So it's a dashed line that goes down like this. And we want to test some points. So I like to test the point 0, 0 to see if it's a true statement. And I get 0 plus 0, and sure enough, that's less than 10. So I need to shade off the line this way. And that kind of makes sense that we have things that are less than 10, then it kind of goes down below. But let's not think about that. Let's think about plugging in a point. And if I was to plug in the point 5, 2, notice I would get 10 plus 10, and we know that's not less than 10. 10 plus 10 is 20, and therefore it doesn't work because it's in the unshaded region. So what happens if I ask a nonlinear inequality? Well, it should be kind of obvious that it's the same as before. So let's say I wanted to graph the function, or not the function, the inequality, y is less than x squared plus 3x plus 2. Now I hope some of you guys can graph this kind of quickly. This is the function x plus 2 and x plus 1. So if I was to go and graph this, I'd have x-intercepts of -2 and -1. It's a positive quadratic, and therefore it goes like this, but I just messed that up because it's not a solid line. Not paying attention to myself. Let's try that again. Let's say y is less than x squared plus 3x plus 2, which means y is less than x plus 2x plus 1. Let's try this one more time here. Let's do a dashed line like I was supposed to. Then what we notice is there is an inside of the parabola and an outside of parabolas. So what we need to figure out is the same as we did before. Where is the solution set? And I like to test the point 0, 0. So if I plugged in the point 0, 0, I get 0 is less than 0 squared plus 0 plus 2. And sure enough, 0 is less than 2, which means it's on the outside of the parabola, and therefore I shade on the outside of the parabola. And the inside of the parabola is the non-solution region. Does not work. But everything on the outside of the parabola will be a solution to this inequality. So let's try what the whole section is actually about. The whole section is actually about a system of equations. And if I were to do a system of equations, what we need to do is we need to graph each line separately. We need to shade the appropriate region for each line separately. But what we should get in most cases, not all cases, what we should get is an intersecting shaded region. It's where two shaded regions overlap each other. That overlap is the solution set to the system. So what does that mean? What if we had the inequalities y is less than x plus 2 and y is greater than or equal to, let's say 4 minus x. Now these are both linear because I want to start us off pretty easy here. If I were to graph, let's change colors for the first inequality. Well, maybe I won't be able to. Pointer options, pen, color. There we go. Let's go with black. All right, if I was to graph y is less than x plus 2, I'm going to go to 2. And because it's a linear function with a slope of 1, I'm going to graph right here. I'm going to go through 2 and 2, negative 2 I mean. And it's less than, so it's a dashed line. And if I test the point 0, 0, I get 0 is less than 2. That's a true statement. So I want to shade down this part of the graph. Then if I was to change the color, if I can find it here, let's change it to, blue's fine. And graph the inequality y is greater than or equal to 4 minus x, I would come up here to 4. And since it's a negative slope, it's going to come over here to 4 as well. And it's an equal to, so I get to draw a solid line. I'm going to do the same thing before. I'm going to test the point 0, 0, and I get 0 is bigger than or equal to 4. That's not true. So that's on the opposite side there. So notice the intersection of my shaded region. So it's everything in here. It's in this little section here, the cross section or the intersection of the two shaded regions. That is the solution set. The set because it's a large group of points, right? It's the solution set to the system. And that's really all you need to do. We could do stuff like this. We're not going to do an exact example, but we could have a linear function and a quadratic function. And if the quadratic shaded inside the parabola and the linear function shaded below, we'd get something that looked like this and something along this line, which meant in here is the solution set to the system. All right, last piece is what's called linear programming. Now, what linear programming is it's a way to minimize or maximize profit, or at least it is in what we do in this particular class in Algebra 1, wherever you're going to see this thing called linear programming. Now, it has nothing to do with computers, but it does have to do with linear equations, or inequalities, actually. So what we need to do is we need to graph and shade the system, just like we did on the last section there. The next step to that is we need to find all of the intersection points. Now what I'm going to make a note of here is the intersection points, or in other words, the corners of the shaded region. Those corners are the points that we're going to use to find the min and max using the what's called the objective function. So what we're going to do is we're going to look at what this might look like. We could have what's called an objective function saying 3x plus 5y. This is my objective function. Then what we're going to have is probably some 4 inequalities. Usually they're all greater than or equal to or less than or equal to. If we were to look at something pretty simple here, let's say x is greater than or equal to 0, and y is greater than or equal to 0. If we were to graph this system, the 4 minus x is going to look like this. It's solid line. The x is bigger than or bigger than or equal to 0. That is the y-axis. And the y is greater than or equal to 0. That is the x-axis. And if you notice that we're going to shade above the x-axis to the right of the y-axis, and what would end up being below the line, we get this shaded region right here. And what we want to figure out is we want to figure out the min and the max given this system and this objective function. And that comes from these corner points, the corners of my shaded region. In this case, the shaded region is nice for us. The 3 points that we need to test are 0, 4, 4, 0, and 0, 0. So what I mean by test is we need to plug it into the, I can't call this p of x, I have to call this the p function. And I need to plug in x equals 0 and y equals 4. If I do that, if I plug in x equals 0, y equals 4, I get a value of 20. If I plug in 4, 0, I get 12 plus 0, I get 12. And if I plug in 0, 0, I get 0. That means the min is 0 at the point 0, 0, and the max is 20 at the point 0, 4. Now, this is basically what we cover in this class. Now, what this could represent is spending. On a real world problem, this could be spending. Like we need to spend less than this amount, but we're obviously going to spend more than 0 and get out more than $0. And what we want to figure out is what's going to be our maximum profit, what's going to be the minimum profit. So obviously if we didn't sell anything, we're not going to get anything, and therefore our minimum profit is going to be 0, and our max profit is going to occur when we sell 0 of these and 4 of these, or something along that line. All right, that actually finishes us off. It finishes us off for the chapter. I'm going to leave you guys with this little bit of nerdism sort of thing, and I will talk to you later.